Hello IB, this is 22E.1, and this is all about compound events. So we're looking at what affects an event, or more than one event, making it compound, and then are they independent events? So does one probability depend on another probability? So compound events are when more than one event is happening at the same time, or one directly after the other. For example, tossing a coin and rolling a die, or pulling two marbles out of a bag. So if you wound up pulling two marbles out of a bag one at a time or one directly after another, it really wouldn't change, except the probability might change whether you replace the marble in between those two draws. So you have to think of how the experiment is set up. For this first experiment we're going to look at is a coin and a die, and we're laying it out in a table. So we have the outcomes for heads or tails and the outcomes for the die, 1 through 6. So if we were just reading this table, probability of a head and a 4 right here is only going to happen once out of all 12 in our sample space. But H or a 4, so a head or a 4, would mean I would need to include all of these possibilities of getting a head. And we also have a 4 with a tail. So that's actually going to be 7 possibilities out of 12 total. So now what we're looking at is, okay, what are our different possibilities and how do we wind up coming up with the probability for a compound event? So for two different events occurring. If you just take a look at a head and a 4, again, a head and a 4, we are looking at 1 out of 12. The head and an odd number, so we have 6 possibilities for a head, but and an odd number would mean I can only include the 5 with the head, the 3 with the head, and the 1 with the head. So if it's an and, it's very specific. So there are 3 out of 12. A tail and a number larger than 1. So a tail being in this bottom row here, and at the same time a number larger than 1. So I can only include 2, 3, 4, 5, and 6. So that's 5 possibilities out of 12. And then a tail and a number less than 3. So a tail and less than 3, so not including 3, so just 2 and 1. So that's 2 out of 12. If we took a look at how we wind up getting this 1 out of 12, if we just identify the probability of A happening, so we're calling A the first event happening, and probability B being the second event happening. So probability of a head is 6 out of 12, or 1/2. And probability of getting a 4, which is our event B, is 2 out of 12, or 1/6. So think about how do we use 1 over 6 and 1 over 2 to get 1 over 12. Let's outline the next one as well. So a head being our first event, A. So again, a head is 6 out of 12, or 1/2. And an odd number would also be 1/2. All right. So already we're starting to see a little bit of a pattern here. If I have my event A probability and event B probability, 1/2 times 1/6 makes 1/12. 1/2 times 1/2 makes 1/4, which is what 3 over 12 reduces down to. And let's see if this holds true for the next two. My probability of a tail would be 6 out of 12, so that's 1/2. And a number larger than 1, all right, a number larger than 1 would include 2, 3, 4, 5, 6. However, since just the probability of a number larger than 1 could be any heads or tails, I would include all of these except for these two, the first two with the 1s. So that would mean 10 out of 12. And if I wind up multiplying those, I would get 10 out of 24, which reduced down to 5 over 12. So again, our pattern has continued. Probability A times probability B gives me my probability of A and B. And let's just test our last one as well. So 1/2 for the probability of a tail, and there are 4 out of 12 for the possibility of getting a number less than 3, so only including 1 and 2. So that would make 4 out of 24, or 2 out of 12. All right, so right now, what we've just connected, is that probability of A, whatever your event A is, multiplied by the probability of B, whatever your event B is, will give you the AND for a compound event, where both events happen at the same time. So if the events are independent, meaning their probabilities do not affect each other, then that could be that they're, something drawn at the same time or one right after the other, but only if the probabilities don't affect each other. So with the marble example, I would have to replace the marble. After I take the first one, I'd have to replace it before I take the second one in order for the probabilities to be independent of each other. Otherwise, when I take that marble out, I change the total number of marbles in a bag, and now I suddenly have changed my probability as well. So they must be independent of each other. So we have to double check how that experiment again is set up. So the notation is probability of A intersect B. So that symbol right here stands for intersect. And every time that we say it, we're thinking and, probability of A and B, so two events happening in conjunction. And if we happen to have more than two events occurring at the same time, we can say all three are independent events and just multiply all three probabilities. So this would extend beyond just two events. So more than one event, we multiply when we have an AND situation or an intersection of events. Just taking a look at this example about Papua New Guinea, if it rains on average 6 days a week, we already know that our probability is going to be 6 out of 7, since there are 7 days in the week. If we're just looking at one specific day, the probability of having one day of rain, again, would be 6 out of 7, because that's what we are given as our average. If we want 2 successive days, that means that the probability that it rains on one day is 6 out of 7. So the probability that it rains on 2 successive days, we'd have to take 6 out of 7, the probability of our first event happening on day 1, and then multiply that by the 6 out of 7, which is the probability of our second event happening, or day 2. So we'd wind up with 36 over 49 for our probability of 2 successive days, and that will continue for 3 successive days. Again, our probability is the same for each of those days. So we just wind up taking 6 over 7 times 6 over 7 and 6 over 7, or we could just write 6 over 7 cubed. All right. Taking a look at this third example, you have 2 photocopiers, and on any day, machine A has an 8% chance of malfunctioning, which means it has a 92% chance of actually working. Machine B has a 12% chance of malfunctioning, or an 88% chance of actually working. So determine the probability that on any one day, both machines will malfunction. So if we're interested in them malfunctioning, we want the probability that they will actually malfunction. So we want machine A to malfunction, which would be our first event. So 8% chance of malfunctioning. So 8%, or 0.08. multiplied by, I also want machine B to malfunction, which is 12%. So then I can find my probability. So think about if I wanted them to work effectively, what percentage would I want to use for each of my events if I want them to actually effectively work. So try this one, finish this one up on your own, and we'll check this one in class. So the other piece to section E is E.2. And now we have compound events. So again, more than one event occurring at the same time, or one right after the other, but they are dependent on each other. So that means one of the probabilities will affect the other event's probability. They do affect each other. So this is like the marbles that I was telling you about. If I pull a marble out and I don't replace it before I draw the second one, it will affect the probability because I have a different total in the bag. So here I'm talking about cards. You've got cards that are labeled 1 to 10. You draw 2 cards out, but you do not replace them in between your drawings. So you could just pull them out at the same time, or you could pull one right out after the other. Either way, it will work out, the same probability. What's the probability of pulling out the card number 4 and then the card number 2? So if I have every card 1 to 10 and each have one number on them, my first probability of getting a 4 would be just 1 out of 10. And I would like to then draw a 2, which would be 1 out of 10 if I put the first card back in. But since I've now taken one card out and kept it out, the next card's probability would be 1 out of 9. So I'd wind up with 1 out of 90 for my probability. A slightly different twist on this is the probability of pulling out 2 cards in any order that happen to have a 4 and a 2 on them. So what we want to be thinking here is that technically I could either be pulling out a 4, then a 2, or I could be pulling out a 2 and then a 4. And we know that if you pull out a 4 and then a 2, it's 1/10 by 1/9, so it's 1/90th. And if you pull out a 2 and then a 4, it's going to be the same, 1/10 by 1/9, or 1/90th. So if I'm saying this could happen or this could happen, I can add those together and just describe it as 2/90ths or 1/45th. So now we start to get into or scenarios where we have more than one possible event that could happen at the same time. To prepare for class, go ahead and try this one on your own. You have a box that contains 4 red and 2 yellow tickets, and 2 tickets are randomly selected from the box, one by one and without replacements. That means we are not replacing in between drawings. So first of all, is that going to be a dependent or an independent scenario? And then go ahead and try to lay out your probability for these 2 situations. All right, we'll see you guys next time.